Hi everyone and welcome back. This time around we will do some compute performance, a little bit of calibration, and we'll see how to get the relative pose of your camera versus the tag we want to locate on, right? So let's get into it. So what I did to basically have a kind of a test set to do some benchmarking is I took like a bunch of pictures of the tag in various conditions, lighting and so on. I put like some lighting from the side or the top or far away, close by, right? So we can know that we have some diversity in the data set. And I build like a kind of a small tester. So what I do first is I load all those images up front, so it doesn't do any I/O when you test your actual code, right? On the platform, it won't do any I/O when it will try to dynamically threshold and detect those tags. And okay, I build a detector. Everything I can do, like basically up front, I do that. And then here you see that I go through all the images, and I do the adaptive threshold straight from the library, from this one, right? I just use it straight, and then. I have to copy the images and so on because it gives them as an output, right? I print the number of detections we got, right? Like all the list of detections, because you could have like several tags on the same image. And then if I don't detect something, I just made myself a little debug thing where it shows which image didn't work, right? So for me, it's to set up like some same test set so I can reproduce over and over my benchmark. Doing so, right, I add like timings, right? Like I made a list of timings there, like for detections and thresholding. And I take the time there and I add the timings on the output side. So I can at the end give us like some statistics and 99 percentiles and so on the timings. So let's see where we are right now. Right? So to do that, don't forget to compile in release mode, right? Like when you are in debug mode, it adds a lot of like bound checks and doesn't actually inline and so on. So -r is the same thing as dash release, right? It's basically build the release. So it loads the images and okay, we got some statistics. We are at 9 milliseconds for the kind of the baseline. So basically using the library and see where we are. And it's kind of absurd. Look at it. Like thresholding is basically longer than detecting the targets. Something is very wrong. And the thing I've noticed during the last video was that this thing allocates a lot, right? Like when you call the thresholding, which is there, right? Look, like if we go inside. Where our output works anyway. Look at that, right? It just allocates on the heap an image. It's kind of stupid for us, right? We are in real time making a video, right? Or like actually thresholding like images from a video. We could use always the same output, so the CPU could basically keep that in cache, or at least all the virtual memory mappings and so on. Like the more you reuse the same spot, right? The more all the memory mechanism, virtual memory caching and so on will actually speed up because you are using the same spot. Okay, I already have that available, right? So that's what I did. So if I check the thing. so basically the first thing I did is I copied those ones. I copied them from the library we are using, and instead of returning an image, which forces an allocation, I ask the user to give me like a multiple reference, so we can change over and over the same image. Did some debugging thing because it was still in process, right? And there I didn't change nothing. It's like literally exactly what the library was doing. And but you see that there are things like this that maybe there is an opportunity. We'll see a little bit later, right? And yeah, so for the integral image, I put an output. Same thing for the adaptive threshold. I also give an output. The integral image is on U32 because you need to be able to add pixels. So let me tell you what it is, an integral image, like quickly. An integral image is basically when you have your pixels, you can generate, instead of having pixel 1, 2, 3, 4, 5, right? You do pixel 1 and then pixel 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3, 4 plus 4, right? It's an integration of on the x-axis and on the y-axis too, right? Like you'll have the sum, but it's also the sum from the top. And that allows like a cool optimization, this algorithm basically, right? Because when you want to do this adaptive thresholding where you want the mean of an area, you can take the two corners, make the difference, and that's basically the sum of what is inside those rectangles, right? So that's an intermediate computation. I didn't change the algorithm at all. I just went through first the architecture, right? Like you've seen that we were allocating. Okay, that's no go, right? Like you need to be able to actually pass images. And then I specialized it a little bit, right? Instead of having like any single images, right? I put like a Luma or a U32. I know what it is, so I don't want to have like I don't know, arrays of RGBs. You can use like straight U32, right? And then once that's done, once the big things are done, right? Like you'll see the next step is going to be like going into micro optimization. So that. Going through this first pass of kind of the architecture side, if we start to do the same thing as before, let's see where we are. Okay, you see we almost double the speed already, right? Just by not allocating. So you see why in Copper I'm insisting so much in robotics, right? Do not allocate, right? And you'll see also that the detections also will improve on the back end of it, right? Again, we're using less cache, we are thrashing less cache, so that also favor other operations, not only the ones you're optimizing, but the ones that are downstream, right? That's counterintuitive, right? You are optimizing one part, but another part that has nothing to do with what you are doing might actually go faster. Okay, so that's already a huge gain. So you see that we are now under the detections, but we can do better, right? And so I continued. You've seen that those things there, right? Like where we still have like a lot of genericity, like this one, right? So I continue to specialize it. And if you look at it now, right? I'll make it. So all that is all specialized. That is also specialized now. That also, right? And you start to see that. Look at the one we had before. Let me see. Well, this one, for example, right? You see that, okay, I use like a U32, boom, straight, and I use like directly the operations, because we don't have like a we don't have like a we don't have like slices and so on in the process, right? Those things can get straight the value. All right. But if we look at where we are with this one, you see that it didn't actually pan out a lot of optimization. So when you've seen things like that where okay, you guess the big things and you start to get stuck, what you need to do is to start to use tools, right? Like immediately, right? Like when you want to optimize, you are often surprised about what is actually slow, and you'll see. I got surprised there too, right? Like I was really surprised what happened. So first, if you want to like hook up a performance monitor, right, on your instrument, your code base, right? You need to be able to have you need to be able to have the debug info in release. Otherwise, you'll get assembly, which is kind of sucks. I mean, you could be good in assembly, but if you add that to your cargo.toml, it means that it will still be optimized, but it will try to match roughly what is where, and that helps to understand what is going on. Then, okay, to be sure, we will recompile with the debug info. It's not to be sure, actually. We need to recompile with the debug info. And then, oh no, I forgot something, sorry. What we need to do is first like clean up any prints we might have. So those ones are good, it's okay, it's during loading, right? But for example, this one we can kill it. We don't want to print anything. We can kill timing because that we will get from the benchmarking, right? And okay, that's pretty good. And here, let's loop, like make an infinite loop basically around the thing we were doing, right? So we do adaptive thresholding. We copy it, and okay, we detect. Okay, yeah. So and now if we okay, those ones are good. I thought I had like other prints somewhere. Yeah, right, like integral image. We don't want to print that, right? Okay. Now let's try to build. Did I forget something? Oh yes, I'm using this. Because we loop, right? It was okay before because we were moving the value. Now we need to use a reference, but it's okay. It's read only, right? So now it should compile. Okay, cool. And if we now what you want to do now that we have the executable is to run that with the Linux Perf tool. It's it will basically go in, and I think it's a sampling profiler. Basically, it gets like at intervals, get statistically where stop basically the program, see where they were, and understand like okay, that was stuck on that instruction or that function and so on, right? So what it will do. Okay, it does the thing, it will loop forever, like we ask it to do, and start to collect statistics about like where this thing is actually spending time on it. You need to wait like a little bit, because like I don't want to have, for example, the loading phase pollute our statistics while it's running. So let it go like, I don't know, 30 seconds or so, and then it should be good enough to get you, I don't know, a few megabytes of sampling data. And you see that it collected like 90, like almost 100,000 samples. So now you have this, this perf data that is actually the index of where it spend time. And there is like an amazing tool with perf. You'll see it's pretty impressive. So you just do perf annotate. It will get by default this perf.data, and it will jump straight to your hotspot. So you see those colors, right? The red is our hotspot. And check this out. It tells us that it spends 34% of its time on this division. I was surprised, right? And you see, wait, maybe we can, you see that that's this division, right? That's division in assembly. It's straight from that line, right? This slash here, right? And it's kind of stupid, because what I do is I get the area, the sum, like what we were seeing, like in the rectangle on the original image, and I divide by the number of pixels, right? And that gives me the mean. And then I compare this mean with the current pixel. So basically, if the current pixel is over the mean, it means that it will be white. If it is under the mean, it's going to be black. And but think about it. That pixel, if we multiply that by W and compare it to the mean, it's the same thing. So this is what I did. So I just removed the division. This, and if you look at the new version, so when we look at when we do those ones, instead of like here dividing, just multiply there, and that's it, right? And let's check how it does now. We are sub 4 milliseconds. So you remember we were longer than the detection, and the detection was at 9 something, right? Now the detection is at 3.4, and we are half the speed like twice the speed of the detection. I think we are really good, right? Like that's exactly what I wanted to see. So you see, your kind of strategy should be the big things, like first, like the big structures, copying bunch of things, or like bad algorithms, right? Then micro optimization with a tool. You cannot guess those ones. The division, I would never have guessed that. I thought like a division was one cycle on the CPU. Apparently it's not. It's just a multiplication is way faster, and we gain like 30% of our timing on this. And then measure and keep that on the side, and then the next step, right? Like if I wanted, like maybe we will do that at some point to have even more performance, would be to actually go and use like vector operations and so on. But I think we should be good enough, right? So what I did next is I tried it on the little platform. I just build it for our target. You remember that from the other videos. And I copy that to the little machine, and we will benchmark that there. So we have like real numbers, because we might be different, right? With the Intel CPU versus the ARM CPU. What I want to see is something reasonable, right? at least like, I don't know, a few times a second, we can actually get this tag and get our position while we are flying. And so we can have like an actual actuation loop that is reasonable. Let me see. So yeah, it's there. So the platform is way slower, right? Like you look at how long it takes to actually load those images. Oh, that's painful. That's why I only put 8 of them. Otherwise, we would like wait forever. Those images are big, so why did I do that? Why did I use like those big resolutions? So we can have like some liberty of like having like more resolution, less resolution, so we can tune a little bit the system depending on, for example, the field of view, right? You will have like a number of like degrees, right? So maybe we will change the length or the resolutions, right? So you see. It's almost like 10x or more, like slower. So 40 milliseconds is really really good. That's I don't know, 20 thresholding per second. Perfect. Detections are a little bit slower, but still it is in the, I don't know, the sum is like in the 5 images per second. We can do better, right? But again, let's start with this, right? And if it misbehaves and we see that we are too slow, we'll improve it later. Next stage. Okay, now we have something that is reasonable, that can run on the platform. We will need to port that to the task. That probably I won't make a video about it. You probably know that, yeah, we will copy paste from one to the other and actually call that. But then we need to to actually localize on that, right? So let's try this. So for this, there is also in the tag library, there is a way to do that, but you need to pass it. You see that? You need to pass it some information. Those. So what it needs some kind of like prior information about your camera and the tags. So first you need to pass it like the real like physical size of your tag. So pass it like it's like 14 centimeters, right? So and then it needs those parameters that are coming from the calibration. So let me walk through that a little bit. So the calibration I used. I used the one from. I used the one from OpenCV. So first you need to generate like a pattern, right? Like so I use like the Charuco pattern. So it's a mix of, it's a kind of a mix of those April tags, but it's Haruko one and like a flat grid. So I'll put that in the repo for you to look at it, right? It's just I'm just using an Charuko board generator and generate that in an image, and you can use it straight. And from there, I made a video. I put that on my little e-ink tablet, and I just, with that tablet, I just go over the entire image. So so it can get like it can get points out of this, and then I run the interactive calibration. It didn't work like straight. I had to make a video, and so you need to provide like some parameters. I'll let you check this out, right? You give it the video, and what does it do is it generates like those like camera parameters.xml, and that's the calibration of your camera. And you can see also the quality of it. Mine is okay. I think it's half a pixel or something of precision, and you get those numbers. adapted them a little bit because I was not the same resolution, right? So you need to make that proportional to the resolution you'll target. If you are not sure, just do that at the resolution you are actually running your computer vision algorithm. So yeah, that's how I got those numbers that I ported to those ones, right? To the ones you've seen there, right? It's roughly half, and that's all the parameters of like an ideal camera, like a pinhole camera. Right, and then what I did is that okay, when we have our loop, I just go through the detections there, and I estimate from those detections the pose out of our parameters. And if you run it, you see that we start to have, a pose with the components, rotation, translation, the relative pose of the camera to the target. Awesome, right? Like that's now we are, and we didn't lose any time out of it. So awesome. Now we have something that is ready to actually localize our drone in space. Now, for the next video, right? We will go into okay, how do we control the drone from that platform? On the CV side, we are done, right? Plus minus the porting. Now we'll get into like how do you communicate with the drone? So we will see that, and how do you make that safe? So you need to be able to take over the drone if something goes wrong. So we'll go into that first, right? Like basically we'll maybe try it with no propeller and then try to hand over the drone from the algorithm to us so we can fly that safely. Okay, I hope you enjoyed that. I hope you learned like a thing or two about how we proceed, right, into like putting an algorithm into a robot. And yeah, hopefully you don't forget to subscribe for the next episode where we'll put these CV things into the real world and try to fly the drone. Thank you so much.